Hello biology students, and welcome to video 4 of the inorganic chemistry unit. So today in video 4 we're going to start talking about solutions, and I want to do some basic vocab first. So a solution is a mixture in which molecules are evenly distributed. So a couple of examples of solutions are something like salt water, where the salt is so evenly distributed in the water that you can't even see it. Similarly, plasma, which is the liquid portion of your blood, has lots of salts and nutrients and enzymes and proteins. Are all mixed evenly in the water that is the basis of plasma. Again, it's evenly distributed. So a couple of other vocab words. When we're talking about any kind of solution, the solute is the thing that's being dissolved, okay? So in our example of salt water, the salt is what's being dissolved. So that's the solute. And then the solvent is the substance that's doing the dissolving, or in which the solute is dissolved. So in this case, in salt water, the solvent would be water. And then one last vocab word for you. Any solution where water is the solvent is called an aqueous solution. Okay. So we already know from video 3 that water is a polar molecule. And there's this phrase in chemistry that we use, and the phrase is like dissolves like. And what that means is that, oops, there shouldn't be an S there, like dissolves like. So what this means is that things that are similar can dissolve in each other. So because water is a polar molecule, it can dissolve other polar things. So some other polar things include sugars. Ionic compounds aren't polar, but they're really similar to polar stuff. So anything that has an ionic bond will dissolve really easily in water. And some proteins are polar too. However, water does not dissolve things that are non-polar, because like dissolves like. They have to be similar to dissolve in one another. So water's polar, so therefore non-polar things like oil will not dissolve in water. Okay, so what I want to look at next a little bit is how water dissolves ionic compounds. Because like I said, ionic compounds are similar to polar molecules in that they have charges. So if you look at this picture over here, you can see here's a picture of an ionic substance, which happens to be NaCl, being dissolved in water. And what I want you to notice is that here is the salt that's undissolved, so this big chunk of salt here. And what's happening is the Na and the Cl of the salt, those two ions are breaking apart, and then they're being surrounded by water molecules. So let's look at this in a little more detail on the next slide. Okay, so NaCl, that's the ionic substance we're looking at. So like I said, if you put it in water, any ionic substance is going to immediately break into its ions. So it's going to break into Na plus and Cl minus. Now the way the water is going to effectively dissolve this is we form what are called spheres of hydration. And that might be a good phrase to write down. So again, that's spheres of hydration. And what literally happens is the water molecules form spheres, or like circles, around the two separated ions. So over here on the Na, the left side, what's going to happen is the water molecules are going to surround the Na, and the oxygens are going to be pointed towards the inside. Okay? And the reason the oxygens are pointed toward the inside is because remember the oxygen end has that slightly negative charge, okay? And then the hydrogen ends have the slightly positive charges. So you can see my positive Na is being surrounded by the negative oxygen. So here, the polarity of water is allowing it to dissolve salt. So similarly on the right side, I'm going to get a sphere of hydration. Only this time, the slightly positive hydrogens are going to be pointed in towards the negative chlorine. Okay, so again, the polarity of water is allowing it to dissolve ionic substances. Okay, so finally that was solutions. So the last little vocab word in this little mini solution section is suspension, which is a little bit different than a solution. So a suspension is a mixture of water and then some stuff that didn't dissolve. So it's when I mix stuff together and some piece remained undissolved. So an example might be blood. So in your blood, there are are gases dissolved in it, in the plasma, but there are also some things that didn't dissolve. So things like large cells. Cells are far too large to dissolve fully in water. Also, very large proteins or anything non-polar is not going to mix and dissolve perfectly in the blood, so that would be a suspension. Okay, so now we're going to move on to the second topic of video 4, which is acids, bases, and pH. So it turns out that water itself can break up into ions. Okay, so here I have a water molecule, and this formula, what you can see here, is called the formula for the dissociation of water. So water can break up into what we call a hydrogen ion, which is an H+. And then if I take away an H+, what's left from water is a hydroxide ion, which is an OH-. Okay, and because whenever water splits up, it's going to form equal amounts of H+ and OH-, the concentrations of those two ions are always equal. Okay. So it turns out that an acid is anything that can break up into its ions and form an H+. So like we saw in the previous slide, water technically can be considered an acid because when it broke up into its ions, an H+ was formed. So an acid we're going to define as any compound that produces hydrogen ions, those H+. And because of that, if I put acids in water, they're going to have high concentrations of H+. There's going to be a lot of extra H+ around. And they also have low pH values below 7. So here's a couple of examples of acids. So we already said, because when water breaks up, it forms H+, so that's water's technically an acid. Another acid, hydrochloric acid, when it breaks up, it's going to form H+ and Cl-, so it's forming H+, so it's an acid. Sulfuric acid can release an H+, acetic acid can release an H+, and nitric acid, just to name a couple of examples. Okay. So quite the opposite of acids are bases, and these are things that accept H+. Okay, so we'll look at what I mean by that in a second. So basic or alkaline. So alkaline just means basic. So basic solutions have low concentrations of H+, because bases combine with H+ to get rid of them. So they're going to have low concentrations of free H+, and they have high pH values. So pH values above 7. Okay, so here we can see water. We already know it's an acid, but it turns out water is also a base because it produces the H+, but it also produces OH-. And you can kind of imagine that what happens is the OH- can combine with H+, so it can accept an H+. Remember we said the definition of a base is something that can accept an H+. So the OH- will accept the H+ or combine with it and then form water again. Okay? So another base, NaOH, again, it's producing this OH, and OH has the ability to combine with H+ that are around. So that means NaOH releases something that can accept an H+, so therefore it's considered a base. Okay. So when this happens, whenever an OH and an H+ or hydrogen ion and hydroxide ion combine to form water, we call that neutralization, because the acidic piece and the basic piece are neutralizing one another. They're canceling one another out to form water. So this is the process of reacting an acid and a base to produce a neutral solution. Okay. So now let's talk a little bit about the pH scale, because I've mentioned it a little bit already. So the pH scale, this measures the relative concentrations of H+ and OH-. So in other words, the pH scale is measuring how much H+ you have compared to OH-. So if you have lots of H+ around, this means you're going to have a low pH value. That means you have an acidic solution. And if you have a low concentration of H+, so you don't have a lot of H+ around, that means the base has combined with that H+ to get rid of it. And you're going to have a high pH value. And the pH scale goes from 0 to 4, with 0 being the absolute most acidic and 14 being the absolute most basic. Okay. So like I said here, 0, highly acidic, 14 would be highly basic, and then 7 in the neutral. Pure water is perfectly neutral. It means it has exactly the same numbers of H+ and OH-, which makes sense because for every water molecule that breaks up into its ions, it's going to form one H+ and one OH-. Okay. So it turns out the pH scale is what we call a log scale. And what this means, if I go from a pH of 1 to a pH of 2, What that means, this change of just 1 in the pH is a change of 10 times in the amount of hydrogen ions. So let's look at this a little more closely so you can understand why we have a change of 10 in the concentration of H plus ions for every change in 1 in the pH scale. So if I have a pH that's equal to 2, what that really means is 1 out of every 10 to the second water molecules in that solution will break up into its ions. Okay, so in other words, 10 to the second is 100. So 1 in 100 water molecules will form an H plus and an OH minus. If I have a pH of 3, what that means is 1 out of every 10 to the third water molecules will break up into its ions. So in other words, 1 out of every 1,000 water molecules will dissociate into its ions. So you can see when I change the pH scale just once, pH of 2 has 10 times more hydrogen ions than a pH of 3. So another example, so if I change my solution, I start with a pH of 9 and I end up with a pH of 7, what this really means is that from 9 to 8, I have 10 times more hydrogen ions. And then from 8 to 7, I have 10 times more hydrogen ions. So 10 times 10. This means when I go from a pH of 9 to a pH of 7, I've increased the number of hydrogen ions in solution that I have by 100 times. So it turns out pH is actually really important in biology, because it turns out all of the reactions in your body really only work at a very, very narrow pH range. The pH range has to be just right in your body for all of our chemical reactions to occur properly. And if you're wondering, well, how do we maintain that pH level if it's so important? And the answer is homeostatic mechanisms. So we use different homeostatic mechanisms to maintain a stable pH so our chemical reactions can occur properly. Okay, this slide just kind of shows you the pH scale and then some common household items that are of that pH. You can see, for example, we know pure water is a pH of 7, but then stuff that's really acidic is stuff like lemon juice, grapefruit juice, tomato juice, and then things that are more basic are things like oven cleaner, bleach, ammonia, etc. So a couple of slides ago I mentioned that we use homeostatic mechanisms to maintain a stable pH, and one of these mechanisms are buffers. Okay, so cells are kept pretty close to a pH of 7 by buffers, and buffers are basically weak acids and weak bases that can help prevent sudden changes in pH. And the way they do this, buffers are able to both accept H plus ions if there's too many around, and they can donate H plus ions if there are too few around. So this helps to keep pH at a stable level in the body. So that's the end of Unit 2, and I'll see you in Unit 3.